For decades, whistleblowers like Bob Lazar have described craft that seemingly ignore the laws of aerodynamics. They report seeing smooth, saucer-like vehicles hovering in complete silence, surrounded by a glowing distortion that looks like a frosted shower screen. These descriptions are usually dismissed as science fiction, but what happens if we stop treating these reports as ghost stories and start treating them as an engineering problem? By analyzing these behaviors through a modern physics framework, we can begin to reverse engineer a grounded blueprint for how such a vehicle might actually function. This chart outlines aerospace propulsion. For a century, flight relied on brute force, rockets and turbines aggressively pushing matter backward. This requires heavy fuel and thousands of moving parts. With single-point thrust, instant, infinite mid-air vector changes are physically impossible. That limitation led our investigation toward a completely different architecture. This is Project Horizon. It operates on a system of programmable electroplasma propulsion. Solving the mystery isn't about discovering a magical anti-gravity engine. It requires entirely redefining what a vehicle is. This exploded view reveals the primary breakthrough. There's no central engine. The multi-layered hull itself is the engine. The top UHTC ceramic layer survives extreme heat and plasma. Deeper, conductive graphene networks instantly distribute the massive thermal and electrical power loads. By combining a resilient ceramic shell with a deeply integrated conductive network, you create a continuous foundation capable of managing massive energy without a single mechanical moving part. Magnifying the whole surface reveals millions of independent microzones. They operate like television pixels, but control energy instead of light. Each pixel contains microelectrodes and a sensor node, reading local temperature and independently ionizing the ambient air immediately surrounding it. When millions of pixels fire simultaneously, they wrap the craft in a highly charged plasma field. This ionized sheath alters the surrounding air's refractive index, creating the exact glowing, blurry shower screen distortion described by historical observers. Achieving true multi-medium traversal, moving seamlessly between space, atmosphere, and ocean, requires us to abandon chemical rocketry and the burden of carrying reaction mass. This baseline excludes the speculative mythology of anti-gravity reactors, the alteration of spacetime, or the use of element 115. The Horizon architecture relies strictly on applied physics, specifically electromagnetic momentum transfer and Lorentz forces. This diagram illustrates field-coupled propulsion. The craft breathes the surrounding environment, ionizing the ambient gas into a plasma sheath, and then using magnetic fields to accelerate that plasma backward to generate thrust. Because this system couples with the external field, it functions across vastly different physical densities, transitioning from atmospheric air to conductive water flow, or utilizing a minimal onboard propellant in a vacuum. This schematic shows how pixels create motion. Stand on one nail, it pierces you. Stand on a million, your weight distributes. Horizon uses this principle. Instead of one massive exhaust jet, millions of microforces collectively push against the air, creating a stable hover. This sequence illustrates how directional flight is achieved. The onboard software pulses the pixel sequentially across the hull, creating a traveling wave of ionization that pulls surrounding air directionally. To pitch, roll, or yaw, software simply adjusts pixel intensity asymmetrically. The flight characteristics reported for decades match the behaviors generated by highly orchestrated, programmable plasma physics. Taking an aircraft built for the sky and slamming it into the ocean at high speed usually results in structural failure. Water is dense, and crossing the boundary between gas and liquid is incredibly violent. This diagram shows how Horizon solves that transition. As the craft approaches water, the programmable skin alters its field strength, creating a stable boundary layer. The hull never impacts the water directly. It maintains a protective envelope that parts the medium. Once submerged, the software shifts across three distinct modes shown here. In air, it uses electro-hydrodynamic flow. Underwater, it switches to magneto-hydrodynamic propulsion, turning salt water into thrust. In the vacuum of space, it utilizes stored propellant for Hall effect plasma propulsion. The vehicle never forcefully pushes through an environment. It actively reshapes the medium around its hull to make infinite traversal across air, water, and space a fluid reality. This schematic compares the Horizon platform to a human occupant. The craft's solid-state design handles extreme acceleration and instant right-angle turns. But without an inertia protection field to decouple mass from momentum, these g-forces would crush a human. The theoretical physics for these forces have been understood for decades. The actual engineering barrier is building a physical structure that can survive the violent, multi-megawatt energy fields required to generate them. Generating continuous plasma sheathing directly against an aerospace hull creates extreme thermal loads and power densities that destroy conventional materials. This illustrates why legacy materials fail. On the left, aerospace metals and superalloys reach melting point limits and soften instantly under multi-megawatt loads. Standard ceramics survive the heat, but their inability to spread thermal energy leads to rapid thermal shock and catastrophic cracking. Tiled heat shields, like those used on the space shuttle, introduce a fatal design flaw. In a high-voltage plasma environment, physical seams between tiles become electrical discontinuities, triggering dielectric breakdown and causing lethal electrical arcing through the hull. To prevent that arcing and survive the plasma loads, the craft requires a continuous, monolithic, and flexible skin built without a single edge or seam. The Horizon architecture integrates propulsion into the structure itself, treating the hull as a highly engineered metamaterial engine. Looking at this cross-section of the skin, the foundational layer is a flexible, ultra-high-temperature ceramic composite. This silicon carbide and zirconium diboride armor survives extreme temperatures without the brittleness of legacy ceramics. Deeper inside is a nano-laminate field layer. This schematic details the core repeat block, alternating conductive titanium nitride and insulating aluminum oxide. This creates anisotropic conductivity, directing electrical energy in specific paths while acting as an absolute insulator to stop microcrack propagation. To manage these loads, the architecture utilizes commercial-grade graphene nanoplatelets, though the graphene itself does not generate the thrust. Instead, it performs two critical functions. First, it acts as a thermal busbar, conducting heat laterally 5 times better than copper to pull energy away from hotspots. Second, the network smooths out charge distribution, eliminating localized voltage spikes that trigger dielectric breakdown. Combining these flexible ceramics with graphene networks allows the skin to handle structural stress, dissipate massive heat, and manage electrical propulsion simultaneously. With the hull surviving the heat, thrust generation is decentralized across millions of independent microzones on the surface. This schematic magnifies the surface to reveal these 5 to 10 micrometer pixels, autonomous control zones embedded directly within the ceramic matrix. Each pixel contains its own microelectrode pair for generating a localized high-voltage field, an embedded sensor node, and an isolated dielectric stack. Propulsion is physics-driven. Phase 1 begins as high-voltage charge builds inside the isolated capacitor layer. Reaching the threshold triggers Phase 2. Field emission drives energy vertically upward through the graphene conductor. Finally, Phase 3 completes with a self-limiting plasma discharge into the ambient medium. This chart connects micro-scale discharge to macro physics. The localized electric field, voltage divided by distance, directly accelerates charged particles, exerting force on them. As these accelerated ions flow backward, their momentum pushes against heavy, neutral ambient molecules to create directed thrust. The reactor merely supplies raw energy to these millions of pixels, which synthesize aerodynamic force locally at the atomic level. This distributed thrust explains the vessel's shape. The disk form is a geometric necessity, placing the center of mass squarely beneath a uniform lift field for perfect hover stability. Generating thrust across the entire skin removes the need for ailerons, rotors, or any other mechanical control surfaces. Instead, the central computer utilizes traveling wave propulsion, firing the surface pixels in rapid, sequential phases that cascade across the hull. This moving wave of ionization physically pulls and pushes the ambient medium directionally across the skin. The central software achieves pitch, roll, and yaw by increasing pixel firing intensity on one side of the craft while decreasing it on the other, vectoring the thrust instantly. Millions of embedded sensor nodes read external air pressure and turbulence in real time, allowing the system to adjust its fields like active noise cancellation for aerodynamics. This system achieves software-defined motion, where the electric field itself functions as an invisible, instantly alterable aerodynamic flight surface. While the theoretical architecture is sound, deployment is currently blocked by two strict physical bottlenecks. The first is power density. Generating multi-megawatt plasma fields requires immense energy. Current batteries and capacitors would be drained in seconds. Sustained atmospheric hover requires a generational leap in compact power generation, such as scalable fusion microreactors that are not yet available. The second constraint is biological. The instant vectoring and infinite degrees of freedom provided by this architecture create extreme, instantaneous acceleration. Without a way to cancel momentum inside the cockpit, the g-forces generated by these directional shifts would be instantly fatal to a human pilot. Until biological resilience or inertial manipulation is mastered, the Horizon architecture is strictly limited to an extreme maneuverability unmanned drone envelope. Building the ultimate exploration vessel requires no new laws of physics. It requires the precise mastery of materials science and programmable solid-state surfaces. Horizon is fundamentally an extreme maneuverability drone. You cannot steer millions of independent pixels using a manual joystick. Controlling a system this complex requires advanced neural interfaces and intent-driven software loops, where the computer interprets high-level commands and orchestrates the physics in real time. Folklore provided the initial inspiration, but the result is a grounded, physics-based blueprint for a machine where the material itself performs the work of the engine. Horizon is a platform designed to go where no human occupant can follow.